The Spitfire that fought the Battle of Britain in 1940 and the Spitfire that fought over Berlin in 1945 shared a name and a silhouette. They shared almost nothing else. In 5 years, the Spitfire doubled its horsepower, changed its wing, changed its engine, changed its propeller, changed its armament, and added a supercharger. It was redesigned at least 24 times. That's not evolution. That's reincarnation. And here's what nobody talks about. Everyone fixates on the Spitfire that existed in the summer of 1940. That beautiful, fragile thing with its 8 rifle-caliber machine guns and its 1,000-horsepower Merlin tearing through formations of Heinkels over Kent. That's the postcard, the tea towel, the pub sign. It's also a snapshot of a single moment in a story that ran for 12 years and 24 chapters. And treating the snapshot as the whole story is like judging a marathon runner by the starting gun. The mark numbers ran from 1 to 24, and each one designated a meaningfully different aircraft. A distinct combination of engine, wing, propeller, armament, and mission. Some were photo-reconnaissance platforms, stripped of guns and painted blue for high altitude. Some were pressurized interceptors, built to fight at 43,000 feet. Some were carrier-borne Seafires with folding wings and arrestor hooks, battered onto flight decks they were never designed for. But every single one of them grew from the same root. An airframe designed in the mid-1930s by a man who wouldn't live to see it fight. The true genius of the Spitfire was never the poetry of the original. It was the original's astonishing capacity to absorb a decade of increasingly violent transformation that would have shaken any lesser airframe to pieces. Reginald Joseph Mitchell arrived at the Spitfire through speed. Pure, obscene Schneider trophy speed. His Supermarine S5 won the trophy in 1927. His S6 won it again in 1929. On September 13th, 1931, his S6B clinched the trophy permanently for Britain at 340 miles per hour, and later pushed the world speed record to 407.5 miles per hour. These weren't elegant machines. They were brutal, enormous Rolls-Royce engines crammed into the smallest fuselage physically possible, their cooling systems threaded through every available surface, including the floats, because there simply wasn't enough conventional radiator area to reject the heat. They existed to go fast, and nothing else. But they taught Mitchell something no wind tunnel or textbook could deliver with the same clarity. The relationship between power, drag, and cooling in extreme regimes. How to make a thin structure absorb enormous aerodynamic and thermal loads without folding. How to squeeze every last mile per hour out of an airframe until the physics said stop. The Schneider racers didn't just inspire the Spitfire, they were its engineering ancestors, and the lessons Mitchell learned from them are written into every structural decision he made. The prototype Spitfire, serial K5054, first flew on 5th March 1936 from Eastleigh Aerodrome. Test pilot Joseph "Mutt" Summers was at the controls. Mitchell watched it fly. He watched the Air Ministry order 310 aircraft. Then, on the 11th of June 1937, he died of rectal cancer. He was 42 years old. He never saw a production Spitfire delivered, never saw the Battle of Britain, never saw a single one of the 23 subsequent marks that would carry his creation through a world war and out the other side. The man who actually guided the Spitfire through its entire wartime evolution, every crisis, every engine swap, every redesign, was Mitchell's successor as Supermarine's chief designer, Joseph Smith. Mitchell gave the Spitfire its bones. Smith gave it its life. and the degree to which Smith's contribution has been overlooked borders on historical negligence. But we'll come to that. First, the engineering. Why could Smith do what he did? Why could this airframe absorb a decade of increasingly radical modifications when so many of its contemporaries hit a wall? It starts with the wing. Mitchell chose an elliptical planform not for beauty, though it is beautiful, but because an elliptical lift distribution minimizes induced drag. That's aerodynamic efficiency at its most fundamental level, spreading the lifting load as evenly as possible across the span, reducing the vortices that bleed energy at the wingtips. The wing was built around a single main spar with a load-bearing leading-edge torsion box in stressed aluminium alloy, giving it extraordinary torsional stiffness relative to its thin cross-section. And that thinness mattered enormously. Roughly 13% thickness-to-chord ratio at the root. Thin enough to keep drag low at high speeds. Thin enough to delay the compressibility effects, the localized shock waves forming over the upper surface that turned other aircraft into coffins in steep dives. The wing's combination of thinness and structural stiffness was central to its high-speed behavior. The fuselage was semi-monocoque duralumin. Structural loads carried through the skin itself rather than through a heavy internal skeleton alone, making it both lighter and stronger than the fabric-over-tube construction still used by the Hurricane. And the engine mounting, here's where the long game reveals itself, had enough physical adaptability that when Rolls-Royce eventually offered the Griffin, a physically larger engine displacing 36.5 litres compared to the Merlin's 27, Supermarine could make it fit. The forward fuselage needed modification. The engine bearers needed reinforcement. But the fundamental structure accepted a power plant it was never drawn to carry. Was this deliberate foresight on Mitchell's part? Probably not entirely. Mitchell designed a clean, structurally rigorous airframe with generous margins because that's what the Schneider racers had hammered into him. You don't design a trophy winner to minimum tolerances. You build it with margin because at 400 miles per hour on floats, anything less kills you. The developmental headroom was an emergent property of that philosophy, not planned, but not accidental either. It was the inevitable result of an engineer who'd spent a decade learning that structures need to survive more than you expect. Joe Smith would exploit every inch of that margin for the next 10 years. The first production Mark I flew on the 14th of May 1938. Powered by the Rolls-Royce Merlin II, producing 1,030 horsepower from 27 litres. Top speed 362 miles per hour. Service ceiling 36,500 feet. Rate of climb 2,530 feet per minute. Armament 8.303-inch Browning machine guns in what was designated the A-wing. 300 rounds per gun, giving roughly 14 seconds of firing time. 14 seconds. That's what stood between a pilot and an empty gun. And the very earliest MKIs left the factory with a fixed pitch, two-blade wooden Watts propeller. This is worth pausing on. Fixed pitch. Wood. A propeller technology essentially unchanged since 1918. Bolted to a 1,030 horsepower engine in 1938. The blade angle was a compromise. Not ideal for takeoff, not ideal for cruise, not ideal for anything. Just acceptable for everything. These were replaced first by de Havilland two-position metal propellers. Fine pitch for takeoff, coarse for cruise. A lever in the cockpit to toggle between two settings. And then, during the Battle of Britain itself, by the Rotol constant speed propeller that automatically adjusted blade pitch across the entire flight envelope, maintaining optimal engine RPM, regardless of speed or altitude. That single swap, same engine, same airframe, different propeller, improved the rate of climb by several hundred feet per minute without touching anything else. The aircraft didn't change. One component changed, and the Spitfire became measurably, meaningfully better at its most critical job, getting to altitude fast enough to intercept incoming bombers. It was the first demonstration of what would become the aircraft's defining characteristic: the capacity to grow by swapping parts, like a chassis that kept accepting better organs. A total of 1,567 Mark I's were built. They were already being superseded before the Battle of Britain ended. The Mark V arrived in early 1941 and became the definitive workhorse. 6,487 built, the highest production run of any single Mark. Its Merlin 45 delivered 1,470 horsepower, a 43% increase over the Mark I. Not a tweak, a transformation in available power from an engine that still fit in the same basic space. But the change that actually rewrote the Spitfire's lethality was in its guns. The B-wing mounted two 20mm Hispano cannon alongside 4.303 Brownings. To anyone who hasn't held these rounds, the difference can sound abstract. It isn't. A 303 round punches holes. A 20mm Hispano shell tears structure apart. The difference isn't incremental. It's categorical. A qualitative leap in lethality. The gap between damaging an aircraft and destroying it. The early Hispano installations were a disaster, though. Mark Burkitt had designed the cannon as a moteur cannon, intended to fire through a propeller shaft. Mounting it on its side, inside the Spitfire's thin wing, fed by a 60-round drum magazine, caused feeding failures under the G-loads of combat maneuvering. The drum couldn't reliably push rounds into a gun turned 90 degrees from its design orientation, while the pilot was pulling 4 or 5 G in a turn. Guns jammed at the worst possible moments. Pilots died with full ammunition trays. The fix came in stages. Belt feed systems replaced the troublesome drums, eliminating the gravity-dependent magazine entirely. Mountings were redesigned with better vibration dampening. The Hispano Mark II arrived with a shorter barrel, better suited to the tight confines of a wing installation. By the time the C-wing appeared, the so-called universal wing, it could accept 4 20mm cannon, or 2 cannon and 4.303Es, or 2 cannon and 2.50 caliber Brownings. Same basic wing structure, different installation packages bolted in at the factory or in the field. The Spitfire's wing had become genuinely modular, a weapons platform that could be reconfigured for the mission rather than fixed at the factory for the life of the airframe. And then everything went wrong. Summer of 1941. The Focke-Wulf FW190A appeared over northern France. Faster in level flight, faster in the roll, faster in the dive. The Mark V was suddenly and emphatically outclassed. For the first time since the worst days of 1940, the RAF was on the wrong end of a qualitative gap, and British pilots were paying for it in blood. The FW190 could dictate every engagement, choose when to attack, choose when to brake, choose when to run, because it held the speed advantage. Mark V pilots couldn't catch it, couldn't outrun it, and couldn't outroll it. The situation was desperate. The Mark IX was born from that desperation, and its development story is one of the cleverest pieces of wartime engineering improvisation ever executed. Supermarine had been developing the Mark VIII. This was the intended next-generation Spitfire, a proper clean-sheet redesign built from the ground up around the new Rolls-Royce Merlin 61 engine. It was going to be the definitive Merlin Spitfire, but the Mark VIII would take months to enter production. Fighter Command didn't have months. Pilots were dying now. So Joe Smith's team did something brilliantly pragmatic. They took the existing Mark V airframe, already in mass production, already understood by every ground crew in fighter command, already supported by a mature supply chain, and fitted the Merlin 61 with the minimum modifications necessary to make it work. No redesigned fuselage, no new wing, no retractable tail wheel. Just the engine, the longer nose section to accommodate it, revised radiator ducting for the intercooler, and get it into the air. The first Mk9s reached operational squadrons in July 1942. Parity with the FW-190 was restored almost overnight. The Merlin 61 was the leap that made this possible, and it deserves its own moment in this story. Where the Merlin 45 used a single-stage two-speed supercharger, one impeller compressing air, two gear ratios to optimize it for different altitudes, the Merlin 61 had a two-stage, two-speed, intercooled system. First impeller compresses the air. Then an intercooler drops the temperature of that compressed charge, before a second impeller compresses it again. Cool, dense air entering the cylinders means more oxygen per stroke. More oxygen means more fuel burned per cycle. More fuel burned means more power. And critically, more power at altitude, where the air is thin and single-stage superchargers are gasping. The Merlin 61 produced 1,565 horsepower. Later 60 series variants, optimized for different altitude bands, pushed to 1,720. This gave rise to the L, F, F, and HF sub-designations that Spitfire enthusiasts already know and debate fiercely. Low altitude, medium altitude, and high altitude variants of the same basic mark, differing primarily in their supercharger tuning and sometimes in clipped or extended wingtips. Top speed jumped to 408 miles per hour. Service ceiling hit 43,000 feet. And because the Mark IX was based on the production Mark V airframe, same jigs, same tooling, same factory floor, output could ramp up fast. They built 5,665 of them, second highest production total of any Mark. From FW-190 crisis to operational squadrons in roughly 12 months. Using the same basic airframe that had first flown 6 years earlier, now producing over 50% more power and flying nearly 50 miles per hour faster. That is the argument for developmental headroom in a single data point. The Mark VIII, the proper Spitfire that was supposed to answer the FW-190, was the clean sheet redesign the Mark IX never was. And this is where the story gets a bit unfair. It had what the Mark IX lacked, a purpose-built design for the new engine, conceived as a whole rather than improvised under pressure. The Mark IX was a brilliant hack. The Mark VIII was the finished thought. But it took the time fighter command did not have. The Mark IX had already solved the crisis the Mark VIII was designed to answer. Urgency writes the narrative, and the Mark IX was the urgent answer. Now. This next part comes from a commenter on this channel, at A Little Bit of Old English, mentioned it after the Tempest video, and it deserves the full telling, because it's the single most dramatic proof of what Mitchell's airframe could endure. By 1943 and 1944, the Royal Aircraft Establishment at Farnborough was running high-speed diving tests to map what happened to aircraft near the speed of sound. This was the ragged edge of aeronautical knowledge: compressibility, shock waves, control reversal, buffet, structural loads that no wind tunnel could fully replicate. They needed a real aircraft going very, very fast. They chose the Spitfire PR-11, a lightweight, unarmed photo reconnaissance variant with a clean airframe stripped of guns, armor plate, and every ounce of unnecessary weight. Optimized for speed and altitude. Nothing to add drag, just engine, fuel, cameras, and pilot. On 27 April 1944, squadron leader Anthony F. Martindale took off in PR-11 EN409 and climbed to extreme altitude. He pushed into a steep dive. The Mach meter, a relatively new instrument fitted specifically for these tests, began climbing. The Spitfire accelerated past 500 miles per hour indicated airspeed, past the point where any design manual said a piston fighter should go. The air over the wings was approaching the local speed of sound. Shock waves were forming on the upper surfaces, disrupting the smooth flow that kept the controls predictable. Buffet was building. The aircraft was entering a regime that belonged to the jet age, in a machine designed before radar existed. At an estimated Mach 0.92, roughly 606 miles per hour true airspeed, the propeller reduction gear failed. Not partially, catastrophically. The entire propeller and reduction gear assembly tore free of the engine and departed the aircraft. Just sit with that for a second. The propeller ripped off a Spitfire, doing Mach 0.92. The nose suddenly lightened by several hundred pounds of spinning metal. The center of gravity shifted violently aft. The engine, still running for a moment before oil pressure collapsed, was now driving nothing. And all of this happened at a speed that no production piston-engined aircraft would match for years. The airframe held, the wings didn't buckle, the fuselage didn't fail. The control surfaces still responded. Martindale recovered from the dive, no small feat with a radically shifted center of gravity and no engine power, oriented toward the nearest airfield, and glided his propellerless Spitfire to a dead-stick landing. He was awarded the Air Force Cross. The propeller broke, the reduction gear broke, the airframe did not. That's developmental headroom measured in Mach numbers. Mitchell designed the structure to fight at 362 miles per hour, and a decade later it survived 606. Not because he foresaw transonic flight, but because he'd built a Schneider Trophy engineer's margins into every spar and skin panel. Margins so generous that the airframe outlasted the components bolted to it. If the Mark 9 absorbed a new supercharger, the Mark 14 absorbed a new identity entirely. Fitting the Griffin into an airframe drawn around the Merlin was not a matter of swapping one engine for another. The Griffin 65 displaced 36.7 litres against the Merlin's 27, a 36% increase in displacement, which meant a physically longer, wider, heavier engine block. The cylinder banks sat higher. The rocker covers protruded beyond the Merlin's profile, requiring bulged cowling panels on both sides of the nose to clear them. One of the visual tells that distinguish a Griffin Spitfire from a Merlin one, even at a distance. The thrust line sat lower relative to the aircraft's centerline, which changed the pitch trim characteristics in ways that demanded a redesigned engine mounting frame. The engine bearers were reinforced, the firewall modified, and the cowling panels completely redrawn. It rotated in the opposite direction to the Merlin, reversing the torque characteristics so violently that careless or inexperienced pilots could swing off the runway on takeoff and never recover. Every muscle memory a Merlin pilot had developed about which rudder pedal to push and when was now wrong. The cooling system needed a rethink too. More horsepower means more waste heat. The Griffin's 2,050 horses generated substantially more thermal energy than any Merlin variant, and the existing radiator installation under the wings had to be enlarged. Deeper scoops, more coolant capacity, bigger oil cooler. without destroying the drag profile that made the Spitfire fast in the first place. Smith's team managed it, but every modification was a negotiation between the airframe's original dimensions and the Griffin's demands. The fact that they made it work at all speaks to the margins Mitchell had built in. The fact that the result was one of the fastest piston fighters of the war speaks to Smith's skill in exploiting them. A 5-blade Rotol propeller replaced the 4-blade unit. Why 5? Because the Griffin's power required more total blade area to convert horsepower into thrust efficiently, and ground clearance limited the propeller's diameter. More blades within the same disc was the only solution. Top speed, 446 to 450 miles per hour. Rate of climb, 4,580 feet per minute, nearly double the Mark I's. The Mark 14 was fast enough to chase down V-1 flying bombs over southern England in the summer of 1944. Those 400 miles per hour pulse jet cruise missiles that conventional fighters struggled to catch. Mark 14 squadrons claimed a significant share of V-1 kills during that frantic campaign. 957 were built. Same basic airframe from 1936. Twice the horsepower. 85 miles per hour faster. An engine that spun the wrong way and barely fit. And it worked. The Spitfire also went to sea, and the marriage was never an easy one. The Seafire, the Naval Spitfire, is the clearest illustration of both the airframe's adaptability and its limits. Adapting a land-based interceptor for carrier operations meant fundamental compromises that Mitchell never anticipated, because he was designing an aircraft to land on grass, not on a pitching deck in the North Atlantic. And yet, the Seafire served throughout the war and beyond. The same lineage, the same elliptical wing in outline, battered, compromised, never quite right for the job, but adaptable enough to do it anyway. The Mark 21 is where the thesis reaches its logical extreme and very nearly snaps. Its wing was completely redesigned, still elliptical in plan form, still recognizably Spitfire to the eye, but structurally new. Thicker gauge alloy skin, revised ailerons with piano hinge attachments, a stronger, wider track undercarriage to handle the ever-increasing weight. Armament was 4 20mm Hispano cannon. Nothing rifle caliber remained. Test pilots had reservations, serious ones. Geoffrey Quill, the man who'd been testing Spitfires since almost the beginning, who'd flown the prototype and every major variant since, raised concerns about the handling. There were genuine discussions within the air staff about whether this aircraft should even carry the Spitfire name. The name Victor was briefly floated. Only 120 were built. The Mark 22 added a bubble canopy, cutting-edge visibility replacing the old framed hood, and a larger tailplane for stability with the heavier Griffin installations. And then, the Mark 24. The final Spitfire. Just 54 built. The last delivered in 1948, 12 years and a lifetime of engineering after K5054 first flew from Eastleigh. It reached 454 miles per hour. It weighed 9,900 pounds loaded against the Mark I's 5,844, over 4,000 pounds heavier. And it was faster, not slower. It carried 4 20mm cannon where the original had carried 8 rifle-caliber machine guns. Same silhouette, same name on the fuselage. Almost nothing else in common with the machine Mitchell had watched take off in 1936. You can track the entire transformation through one component alone, and it's the one bolted to the nose. The propeller went from a fixed-pitch wooden 2-blade Watts unit, unchanged since the First World War, to a de Havilland 2-position metal prop, to the Rotol constant-speed three-blade that transformed the Mark I's climb performance during the Battle of Britain, to 4 blades for the early Griffin installations, to 5 for the Mark XIV, and finally to contra-rotating 6-blade assemblies on the Griffin 85-powered variants, producing 2,375 horsepower. One component, one lineage. Fixed wood to contra-rotating metal. The entire arc of the Spitfire's evolution compressed into the thing spinning at the front. This capacity for reinvention was not normal. Other fighters hit walls, hard ones. The Hurricane's fabric-covered fuselage and thick wing limited its speed potential so severely that its final operational variant was a ground attack platform. Sturdy, useful, still dangerous with rockets and bombs, but no longer competitive in air-to-air combat against anything modern. It had been a war-winning fighter in 1940. By 1943, it was an attack aircraft. The airframe had nowhere left to go. The Bf-109 evolved impressively from the E through the G and K, reaching over 2,000 horsepower with methanol water injection in its last variants. But it paid for every increment. Its narrow-track undercarriage, a design constraint baked in from the original structure, became increasingly lethal as weight grew. Landing accidents in late-model 109s were endemic and well documented. Pilots feared the ground more than the enemy. Its compact fuselage constrained what engines could physically fit and limited fuel capacity. Messerschmitt squeezed extraordinary performance from the design, but the ceiling was closing in. The P-40's Allison engine lacked an effective high-altitude supercharger, capping the airframe's useful combat potential above roughly 15,000 feet. Below that altitude, it was a tough, capable fighter. Above it, the engine was simply running out of air. And in the European theatre, where combat routinely happened above 20,000 feet, that was a fatal limitation. Each of these was a fine aircraft that served its nation with distinction. None of this is about rankings or national pride. It's about structural engineering constraints. But each hit a developmental ceiling imposed by its original design decisions. The Spitfire kept accepting new engines, new propellers, new wings, new armament, and it kept working. That capacity is the story. And there's an injustice at the centre of it that deserves correcting. Mitchell gets the romantic credit. He's the genius who designed the Spitfire, and he was. His Schneider Trophy lineage, his instinct for structural rigour, his choice of the elliptical wing, all foundational. His death at 42, before he could see what his creation would become, adds a tragic poetry that the British public has never stopped responding to. All of that is earned. But he died before a single production Spitfire reached a squadron. Every wartime mark, every adaptation, every crisis response, every engine change and wing redesign and propeller upgrade was developed under Joe Smith. The Mark V's engine change, the Mark IX's desperate improvisation to counter the FW-190, the Griffin installation that required rethinking the entire forward fuselage, its cowling, its engine bearers, its cooling system, and its structural loads. The universal wing. The Mark XXI's complete redesign. All Smith. All done under wartime pressure, while factories produced aircraft in the thousands, and his engineering team was redesigning the next variant in parallel. Smith once described the process of developing the Spitfire as being like building onto a beautiful house, adding rooms and modernizations while keeping the essential structure intact. That analogy understates what he did. He didn't just add a conservatory, he doubled the horsepower, changed the engine twice, redesigned the wing, transformed the armament, and kept the aircraft competitive against opponents that were themselves evolving as fast as their designers could manage. He wasn't a custodian of Mitchell's legacy. He was the engineer who found and exploited every ounce of potential that Mitchell's design contained. Without Mitchell, there's no Spitfire. Without Smith, there's only ever the Mark I. So let's put the numbers side by side, because this is, at its core, an engineering argument. And engineering arguments are settled with evidence, not sentiment. Mitchell designed an airframe in the mid-1930s that was still being improved in the late 1940s. Horsepower went from 1,030 to over 2,050, and to 2,375 in the final Griffin 85 variants. Speed went from 362 miles per hour to 454. Weight went from 5,844 pounds to 9,900, nearly doubling, and the aircraft got faster, not slower, because every additional pound was offset by the additional power and aerodynamic refinement that the airframe accepted without complaint. Armament went from 8.303-inch rifle-caliber machine guns to 4 20mm cannon. The propeller went from a fixed-pitch wooden relic of the First World War to contra-rotating metal blades, absorbing over 2,000 horsepower. The supercharger went from single-stage 2-speed to two-stage 2-speed intercooled. The wing went from the A-type carrying only machine guns, through the B-wing with its troublesome drum-fed cannon, through the universal C-wing accepting any configuration, to a structurally new wing on the final marks. Over 20,000 Spitfires were built across all variants, and one of them survived a dive at Mach 0.92 with its propeller torn off and its pilot alive to land it. 24 marks. 24 distinct configurations of engine, wing, propeller and armament. 24 different aircraft wearing the same name and the same elliptical silhouette. The ultimate measure of a great design isn't how good it was on day 1, it's how much room it left for day 2, and day 200, and day 2000. Mitchell, knowingly or not, through instinct born of a decade of racing seaplanes at speeds that killed careless engineers, designed an airframe with more developmental headroom than anything else in the sky. Smith spent 10 years filling that space, mark by mark, engine by engine, crisis by crisis, propeller by propeller, until the aircraft that bore Mitchell's original outline had become something its creator could barely have recognized. The Spitfire wasn't one legend, it was 24. And the gap between the first and the last, 92 miles per hour, 1,000 extra horsepower, 4,000 additional pounds, an entirely different weapon system, is the real story. Not the romance of 1940, not the stirring music and the sunlit contrails. The relentless, unglamorous, brilliant engineering that kept this airframe relevant for a decade, when everything around it was changing at the speed of war. If you want more stories told this way, engineering over nostalgia, evidence over mythology, subscribe. There's plenty more to build.